PhD candidate at RBC CPS IISc. So today I will be presenting my PhD colloquium on time series prediction for intent-aware robot learning. So I will walk you through the motivation, problem formulation, the models I proposed with results and conclusion. So time series prediction mostly deals with how to predict future data given the past data. It's broadly classified into direct prediction, recursive prediction, univariate and multivariate predictions. There are other classifications also, but these are the major classifications. The application ranges from extended reality, where a prediction is smoothens gaming experience, to human-robot interaction for safe and efficient handovers, collision avoidance in autonomous driving, to aviation, finance, weather prediction, and so on. So earlier methods used regression-based extrapolation, like velocity-based quadratic or linear extrapolation, then classical kinematics with constant velocity jerk models, then template matching techniques. Then we have Bayesian frameworks, like basically Bayesian models and Kalman filters, which probabilistically models the data to predict future states. Then we have RNNs and LSTMs, which are widely used to predict time series data. Parallelly, in robotics, imitation learning is being used to make the robot learn from human demonstrations. And recently, transformer models are there, which actually was built for NLP task, but recently, like from a couple of years back, they are being used for time series prediction as well. And of course, there are many hybrid models, which are a combination of most of these, between any of these frameworks. So given the diverse time series models, I benchmarked them from regression Kalman filters to imitation learning and transformer based models. I introduced sampling based maximum entropy inverse reinforcement learning with a novel sampling strategy for real time target prediction in extended reality. Then I designed a framework using maximum entropy deep inverse reinforcement learning for fast and accurate handovers, to which I extended to multimodal and multi-agent prediction. Finally, I proposed a Bayesian transformer, BibTrap, which is used to predict time series data and is applied to handover and walking trajectory scenarios. So coming to time series intent prediction for pointing tasks in extended reality, the main challenge is the targets are very closely spaced in a 3D environment. So if you use traditional regression-based methods in 2D, it works, but if you consider the Z coordinates, it's a little difficult to predict the target. So here we proposed a sampling-based maximum entropy inverse reinforcement learning, or SMAERL, which maximizes the log likelihood of expert demonstrations. And the likelihood of expert demonstrations comes from the principle of maximum entropy. So there's a whole lot of derivation. I've just written the final expression. So from here, we can see that the probability of a trajectory is exponentially more likely to occur given the reward of that trajectory. So for each so here basically the Z is the state partition function, which is estimated using sample trajectories. So for each expert trajectory in the expert data set, we generate some sample trajectories and we estimate the state partition function using these sample trajectories. Then we substitute this equation of the likelihood into the objective function, and the gradient of which is given by the after some calculations, we see that the gradient is and assuming linear feature reward dependency, we see that the gradient is given by the difference between expert features and the sample features. So the features that we used here are specific to rapid aiming tasks. So both the pointing task as well as the handover task comes under the category of rapid aiming task, which has certain properties. So basically, these features, they define how the task has been carried out. So suppose the users take shortest path as possible. So the distance feature captures any deviation from the shortest path. Similarly, we have a velocity feature. So what we did is that we plotted the velocity profiles of the user with respect to the distance from the target, and we fit various polynomials, and we see that quadratic polynomial kind of averages the average velocity profile. So this velocity feature captures any deviation from the desired velocity profile. Similarly, we have acceleration and jerk feature. So here are the results of accuracy and sensitivity. That is the number of correct predictions versus the input. So we see that during initial part of the demonstration, different users demonstrate different velocities and different profiles. So the sample feature, so the sampler doesn't able to capture well the expert demonstration. So the accuracy of SMARL is comparatively less during initial 20 to 25% of the task.
So handing over a baton in a relay race.
Yeah, it's kind of, but here we are handing over to the robot. I will just show you in the coming video. Yeah, so the initial part when the input is less, we see that SMRL has lower accuracy and sensitivity. But as the input increases, SMRL performs better as compared to other state-of-the-art methods, and like up till 70% of the task. But after that, we see that CMK5, that is classical kinematics of motion, it performs better because it has already seen a lot of data and there's only few data that is left to be predicted. So CMK5 performs better. And similar trend has been observed in VR as well. So here's the plot of variation of accuracy versus average velocity and accuracy at FCP, that is full convergence point. So if any algorithm reaches 99.9% accuracy, it's a technical term which we call at full convergence point. So full convergence point that is achieved by CMK5, we see that accuracy of SMARL is greater than MADRL, which is greater than SVM, and from the velocity curve, we see that the hand velocity is increases and decreases. So it's on an average, it remains constant with respect to the hand velocity. So here's the demo of the pointing graph. So the green color is the ground truth, and the blue color is the predicted rates. Yeah, and the blue color is the predicted target from the algorithm. You can see that the targets are very closely spaced even in Z coordinates, and so and the hand is getting tracked using motion capture system, which is sent to the backend. So here you can also see a wrong prediction example. So I'm wearing a marker which is tracked by motion capture system, and those markers are sending the hand coordinates to the algorithm, and the algorithm is predicting the intended target. So from XR to human robots interaction. So here the challenge is we have less data. So here the challenge is we have less data and with high variability. So our aim is to devise a algorithm which could predict data with less which could accurately predict the intent with less data. So we used a framework using maximum entropy deep inverse reinforcement learning, which uses a neural network to estimate the reward parameters. So the objective function almost remains the same, that is to maximize the joint posterior distributions of the reward parameters within a given reward structure. And if we take the gradient is given by the difference between the state visitation frequency and of the expert and the expected state visitation frequency of the learner, and the gradient is backpropagated through the neural network to learn the optimal reward weights. So here's the algorithm in short. So first we have initialized an MDP with a value function, and then we use approximate value iteration and Polish propagation algorithm to calculate the probability of a given trajectory, basically the partial trajectory given the goal state. And then we use Bayes theorem to calculate the probability of a goal given the partial trajectory. So here we assume that all the targets are uniform. That is, we assume the uniform prior over the targets. And at the end, the goal which has the highest probability is the predicted target. So this is the result. So we see that initially both MADRL and SMARL performed similarly, but later on MADRL achieved higher accuracy till around 45 to 46% of the input, and then so basically, and also MADRL reaches FCP at around 80 to 90% of the task. So from the FCP plot, it is more clear. So at FCP of MADRL, we see that the accuracy of SMARL is almost similar to that of PIRL, that is path integral inverse reinforcement learning. So I've compared these methods with other methods which are used specifically used for human to robot handover. And CMK5 reports the lowest accuracy over here. And again, the plot was the plot of average accuracy versus velocity. We see that it's almost constant with respect to the hand velocity. So here is the demo. So this work was accepted at ICRA 2024. So just forward it a little bit. Yeah. So here are the hand motion is the hand coordinates are collected through Google Media Pipe, which is through a webcam at the top, and the ground truth is the color of like which is shown on the TV, and the same color bowls are kept around the robot, and the similar color blocks were given to the user. So the task of the user was to see the ground truth color from the TV and pick that same color and try to like drop it at the same at the corresponding bowl. And but the robot doesn't know where the bowl is or like what is the color of the bowl. So basically, the robot only knows the hand coordinates of the user, and based on that, it predicts like where the user is trying to reach. And ultimately, we calculate like how many correct blocks were there in their corresponding balls to calculate the accuracy. So later on, we extended this algorithm to a higher degree of freedom robot also. It's lagging a little bit, but yeah. So there are sometimes incorrect predictions also, like we are moving our hand somewhere and the robot is going somewhere else. It might be due to various reasons, like due to algorithmic error also, or like due to fault tracking. So till now, we have seen two algorithms, that is SMARL and MADRL, applied for time series prediction, applied to two different tasks, that is pointing task and human to robot handover. So from here, we see that SMARL has faster convergence compared to MADRL. It is because SMARL has one-shot sampling process for estimating the state partition function. Whereas training the neural network in MADRL is time consuming. So yeah, SMRL has faster convergence, and also from the accuracy, at 90% task completion, we see that SMRL is giving good results for pointing tasks, whereas MADRL was better for human to robot handover scenarios. Yeah, and this work was accepted at ACM transactions in human robot interaction. So in the previous method, we see that we have assumed an uniform prior distribution, but here we argued that intent could be also, very like we can gain a lot of information about user intent by using data from multiple modalities. So instead of using only hand motion, we have taken data from eye gaze as well, using average fixation duration, and we calculated the prior probability of the goals. And the rest of the algorithm remains same. And using Bayes' theorem, we again calculated the probability of a goal given the partial hand trajectory. And here are the results. So we see that the accuracy of both the multimodal as well as the unimodal method is same during the initial 20 to 25% of the task. But later on, the accuracy of multimodal algorithm, that is in green color, using hand plus eye, is greater compared to that of using only hand motion, and the sensitivity is highest, remains higher throughout the pointing task. So at FCP, so here from here, again, we can see that both the algorithm reaches FCP, but hand plus eye, that is multimodal algorithm, reaches FCP much earlier compared to hand motion. So at FCP of multimodal algorithm, we see that the unimodal case using only hand motion achieves only 90% of the accuracy. And also from the variation of velocity, variation of accuracy versus velocity, we see that the accuracy slightly increases. But for the previous result, we have reduced that the velocity, the accuracy almost remains constant. So here the increase in accuracy is only due to the incorporation of eye gaze, and also and the prior probability obtained using average fixation duration. But eye gaze has an is usually affected by divergence effect. And it makes the prior a little corrupt, but the strong likelihood from hand motion overcomes the corrupt prior, and ultimately the accuracy increases. So here is the task. So the setup remains the same, but one thing is added, and that is the user is also wearing eye tracker, and you can see that where the user is looking from here. And then we have calculated the average fixation duration from the. So there's a formula, like a number of fixations divided by number of fixation duration by total number of fixations. And using that, we obtained the prior and we predicted the target. So Yeah, so if till now we have seen unimodal prediction and multimodal prediction, now we go to multi-agent prediction. So so till now what we were seeing is that we were just concerned about the hand data. We are predicting the hand motion and then asking the robot to come to that location and take the object from the user. But here, if we consider specific to the human robot handover, we have seen like we can see that there are multiple agents interacting. So like one is the user, of course, and the other one is robot. So instead of using only user to predict the intent, we can use the complete interaction between the robot and the user to predict. So often, if you see in other scenarios as well, predictions involve multiple factors which are not directly visible in the observation space. Like a particular degree of freedom might be might be affected by other variables or other degrees of freedom as well, which are not directly visible. So we need to kind of zoom in into the data, or in other words, I could say that we have to, we can project the data to a higher dimension to observe some, correlation between the data which is not directly visible in the main observation space. So in this case, we used an extended version of Bayesian interaction primitives with a set of features that we called as feature-based Bayesian interaction primitives. So we added each. So I will explain the algorithm in the next slide. In this slide I will explain you the experimental setup. So we added each features that we discussed previously as an additional degrees of freedom, and then we implemented FBIP, and basically we implemented the scenario in robot assisted manufacturing, which involves like assembly and disassembly process of a knuckle joint. So why knuckle joint is taken that we need to keep the setup same with the 4 targets. Later on, we have extended to higher degrees of freedom. So the knuckle joint has 4 components. One is knuckle pin, taper. The other one is taper pin, eye, and fork end. So there are 4 components, and the assembly task involves the human to take the object from the robot, and the disassembly task is the user is giving the object to the robot. The robot knows where the components are kept, but is like which component has been kept where. Yeah. So and like then we have created a mixed reality interface where we have integrated various features of the assembly and disassembly task, and it also involves the combination of both the pointing tasks that have been working on, that is pointing tasks in extended reality, like to click the buttons in the interface, and of course the human to robot handover prediction. So what we do is that first we, as I've told, first we project the data to a higher dimensional basis space. So each degree of freedom was projected to a higher dimension using the basis matrix, which consists of a sequence of Gaussians evaluated at different phase values, which is linearly mapped from 0 to 1. So BI is the dimension of the basis space. And then once the data is projected to the basis space, we learn some weights in the basis space, and then we project the data back to the observation space using this nonlinear observation function H. And the weights in the basis space was estimated using least square regression. So this is the expression. So we need some kind of methods to jointly estimate the basic like to capture the spatiotemporal aspects of the weight, and then to update the like weights and predict the data. So for this, we jointly estimate the phase velocity, and weights together, and we combine them as a state, and we implement extended Kalman filter to iteratively and recursively predict the states of the data. So once the data has been predicted, we transfer it back to the observation space, and finally we got the predicted trajectory. So here is the like pipeline. So this is so first is the basis space representation from demonstration, and then all the data set has been converted to the like through the basis matrix that has been projected to the basis space, and then we learned the weights using extended Kalman filter, and finally there's prediction, and all these prediction and all they are visible in real time through a user interface, so that the user could get real time prediction. So we validated the proposed approach into open source dataset. So it is a little difficult to get open source dataset in this kind of scenarios, because every experiment has its own robot, and like basically the data is very much specific to the robot and to the experimental setup. But yeah, we get two open source data set. One is robot to robot. The other one is hand to hand data, which can. So the robot to robot data consists of two UR5 robots. Okay, like giving handing over objects to each other. So we have 200 expert trajectories, out of which 180 were used for training and rest for testing. Similarly, hand-to-hand data, like users giving object to another user, and we have 238 expert trajectories, and 198 were used for training and rest for testing. And so we compared evaluated the method on these two data sets, and basically we obtained so from here we can see that FBA obtained lesser mean absolute error, both translational as well as rotational on both the data sets.
So, excuse me.
Yeah.
What do you mean by robot to robot expert trajectory? What does that mean? Expert trajectory?
So here in like expert trajectory throughout this work, throughout my thesis, like it means that like the demonstration, like the ground truth demonstrations is called the expert trajectory. So our whole aim is to learn from those ground truth data, and then given any new scenario, the robot should behave as the expert. So that's why we call the ground truth data the expert data.
These trajectories are presented in what form? They are videos or?
Actually, some work they have done in video, but these are normal, like the joint coordinates of the robots and the XYZ coordinates, XYZ roll pitch of the hand. So it's like that.
And how are these obtained? By some AMUs of the robot?
Yeah, so basically, robot has its own SDK through which we could get the robot coordinates. For the hand, we have used multiple sensors. Like first, we have used a simple Google Media Pipe to track the hand coordinates. Then we have used IMU sensor, basically a vibe tracker, which is an IMU sensor to obtain the XYZ roll pitch of the hand coordinates. And the data is in Cartesian, and so we didn't use videos to train our model. We used the raw XYZ data. Yeah. So we see that during initial, up to around 40 to 50% of the task, FBAP performed better, but later on its accuracy is less as compared to MADRL. So we kind of, so like to implement it in real time, we used a hybrid FBAP plus MADRL based method, to calculate the accuracy and all. And we also see that so DTW cost is dynamic time warping. So the DTW cost of FBAP is comparatively lower than other methods. So, and also we obtained a safety index, which is again a standard metric, which is a combination of accuracy and DTW cost. And we see that the hybrid method has higher safety index as compared to other methods. And we also taken user feedback on TLX, as a task load index and system usability scale from of the system from the user, and we see that the task load index is low because the different components were integrated into a single environment for prediction, like both the assembly, disassembly, and also the mixed reality environment shows what is the next component that the user should pick and place. So although that's why the task load index is low, but since there are multiple predictions like hand prediction for the pointing task and also for the human robot handover, the system lags sometimes, and hence the I think that's the reason why the SES is less. So this is a video of assembly task. So the user is so based on the partial hand motion of the user, the robot is going to the user and giving the object, and then the user will finally assemble the task. And the disassembly process is just the opposite, that the user is giving some object to the robot, and based on the partial motion, the robot comes and places it at the intended target.
So what is the sensor that is sensing the user's hand here? Is
So
it camera?
Yeah, so here in the tripod, there's one camera on the top, and we are using Google Media Pipe to track the hand motion. Later on, after this work, when I will show about the high degree of freedom robot, there we are using a vibe tracker, which is a IMU sensor to track the hand coordinates. So it's a 3 degree of freedom robot, so we don't need the roll pitch here. But when we go to high degree of freedom robot, we need the role pitch yaw also. So basically there we use IMU sensor. It's the mixed reality interface that we do, like we created. So here you can see that the user isn't completely touching the buttons. Like with just the partial motion, the buttons are already selected based on the prediction, and then the robot does the action that has been assigned to it. So coming to last part of my work. So for that is time series prediction using transformer. So basically, transformer, due to their self-attention, long-range dependency, like long-range dependency modeling in time series data. So basically, they are originally proposed for NLP task, but recently they are being used for predicting time series data. So some variants of time series transformer include informer, autoformer, fedformer, okay, which improve efficiency using sparse, sparse self-attention, decomposition, and Fourier transform respectively. But unlike point-wise tokenization in most of the NLP tasks, time series data has local semantic information as well. So which these transformers are not good at capturing those local semantic information. So PASH-TST, which is basically the state of the art for like a state of the art time series transformer, captures this local semantic information through patches, like it discretizes the entire input univariate input sequence into patches, and then it uses to predict the data. So, but still the dependencies were captured through self-attention, but now over like tokenized segments or patches. So in case of small or variable data sets, there is high variance and a poor inductive bias. So we thought of embedding the spatiotemporal aspects of the data through a phase-aligned phase-aligned low variance manifold, which will reduce the variance and also at the same time will capture the canonical dynamics of the system or the data set. So we propose a patient interaction primitives based transformer that is WIP-trap for time series prediction. So here what we do is that we kind of so here we took motivation from a previous approach using Bayesian interaction primitives, and we combine it with transformer to predict future data. So we project the trajectories into a higher dimensional basis space, and then we learn the basis space using ensemble Bayesian interaction primitives. Then we applied patching and passed this through a transformer encoder to predict future data. So BIP BibTrap consists of these 3 to 4 steps. First is basis space representation, then spatiotemporal updates of basis weights, then trajectory refinement via forward, backward, exponential smoothing, finally patching and transformer encoding before the final forecasting. So we have a multivariate series, okay, and we split the data, like basically degree of freedom of the multivariate series, and we pass it through a uh, and we basically project it to a higher dimensional basis space using Gaussian basis function, which is evaluated at different phase values between 0 and 1 with different centers and variance. So we have projected the data to this higher dimensional basis space, and we learned the initial weights using least square regression, and then we iteratively predict one step, and then again update it using Bayesian interaction primitives and ensemble Carnot filters. So we repeat this process multiple times, basically n times, where n is the look ahead horizon or the intermediate prediction length, you could say. So this is the intermediate trajectory that we get. So this intermediate trajectory has preserved the spatiotemporal features or information of the data set, and this has to be embedded to the input sequence. And we use forward backward exponential smoothing to kind of embed the this is spatiotemporal data to the input. So here we can see that the blue color is the input trajectory, the original input trajectory, and the red color is the predicted intermediate trajectory through BIP and N symbol Kalman filter in the base space. And the green color is the smooth head trajectory. And then we send this smooth head trajectory to the transformer encoder. But before sending, we patch the data, which reduces token size and computational cost, which has been proved in that patch TST work. And then we normalize it. And then we embed it with positional embedding. And then we send it to a transformer encoder. So this work is the transformer part is a standard method. So it's not like something new that I proposed. So the equations are standard equations where so we are using multi-head self-attention mechanism, which calculate the attention scores. And then we pass the data through a linear. So basically, first we flatten the data and we pass it through a linear layer to predict the future trajectory. The model was retrained on ETTH1 dataset, which is electricity transformer temperature dataset, and was fine-tuned on the HRH, and that is human robot handover, and a walking trajectory dataset with a mean square error loss. So the HRH and walking trajectory dataset is thing that we collected. So the HRH dataset consists of humans handing over different objects to the fixed space manipulator. So there were total 6 participants and different objects.
So that the previous slide.
Yeah.
So the previous one. So here you have a prediction. So you read.
Okay.
How did you verify the quality of the prediction?
The intermediate prediction. The intermediate prediction actually we didn't verify. Okay, yeah. So we kind of not directly, but rather we did a lot of ablation studies by fine tuning the value of. So basically, that intermediate trajectory specifically we didn't verify, but the final prediction we validated by changing these parameters like the prediction length, the prediction horizon, that is n over here, and the smoothing constant alpha and all. But the intermediate trajectory prediction. Yeah. So that's what as Sir is telling. We have calculated the RMC and DFT scores of the final prediction that I will show you. But this intermediate trajectory we haven't evaluated. But yeah, it's a good suggestion. Different objects to a fixed space manipulator, and we collected data from 6 participants with different objects like plier, screwdriver, water bottle, with tape, battery, charger, etc. And we recorded the data at 30 Hz frequency. And there were so each participant was asked to demonstrate 100 trajectories through kinesthetic demonstrations. And there were total 18 degrees of freedom, basically 6 for the hand motion, XYZ roll pitch yaw. Yeah, like 6 for hand motion, 6 for robot task space, and 6 for robot joint space. So total 18 degrees of freedom, and 500 data were used for training and rest for testing. So we reported 10-fold cross validation results. And we also evaluated the method on walking trajectory dataset, which Naveen collected, where we asked the humans to walk freely within a closed environment, and we track the position of the human basically. And so there are total 4 degrees of freedom, that is the XY coordinate of the user, and the velocity and acceleration. Yeah, and the data was recorded at 5 Hertz. So there are a total of 122 trajectories, out of which 100 was used for training and remaining for testing. So this is the data that we collected. So like this, using kinesthetic demonstrations. That is, so here we can see that the user is wearing a white tracker, okay, in the hand. So which is a kind of IMU sensor, which is used to get the XYZ roll pitch yaw coordinates of the user. It's lagging. So these are the correct demonstrations. So we can see that the user is handing over different objects to the robot, and based on the partial track motion, the robot is going to the predicted location, and then taking over the object from the users. And there are some cases of incorrect prediction as well. So yeah, so we evaluated the final prediction using 2 metrics. One is RMSE, and the other one is DF, which is discrete facial distance. So RMSE is used to calculate the point-wise accuracy or the error, and whereas DFD captures the overall shape of the trajectory. So we see that when the input is less, EBIP, due to its strong Bayesian prior, captures the dynamics, the spatiotemporal dynamics of the data, and it has it has lower RMSE compared to other methods. But as the input increases, BibTrap and PatchGST, they perform better because they are transformer-based model. Especially BibTrap performs the best because it also has the patient prior. So the combined effect makes its prediction more robust. So yeah, so the BIP type performs best with at 60 to 90% of the input. If we see the DFD scores, there's a little complementary trend like DFD performs. So with patch TST, we see that the DFD is lesser like throughout. So lesser DFD means that the shape is better predicted. Whereas BibTrap, it has comparatively higher DFD as compared to patch TST because BibTrap, due to like it regularizes away the small fluctuations due to smoothing. Coming to walking trajectory prediction, in RMSE, similar trend has been observed. That is, at 30% input, EBIP performs better, whereas at 60 and 90% input, BibTrap has lower RMSE than patch TST because it kind of takes it leverages both like the advantages of EBIP with a strong prior as well as the transformer architecture. And for comparing the DFD scores, we see that at 30%, patch TST has lower DFD than BibTrap because the prior in BibTrap pulled the predictions towards the canonical average, like a canonical walking motion, which induces a phase shift, and due to which the DFD increases. And with more data at 60 to 90%, patch TST with less spatiotemporal knowledge, basically the amplitude or the amplitude of the wrong prediction it accumulates, which results in higher phase drift and consequently higher DFD than BibTrap. In summary, first seeing various time series prediction models from regression Kalman filters to imitation learning, that is IL-based methods to transformers architecture. Then we saw SMRL for pointing task in extended reality, and then we discussed about time series prediction in human robot handover. We saw that MLERL performed best in handover scenarios. Then we also used, instead of using only hand motion, we have used multimodal cues to predict data using hand and eye gaze. Then we went to multi-agent time series prediction, where instead of using only hand motion, we are using the interaction between hand and the robot to predict the data. And finally, we concluded with time series transformer BibTrap, which uses like a Bayesian interaction primitives along with transformer to predict data. And we saw that BibTrap, provides the most balanced trade-off between temporal accuracy and shape fidelity. So yeah, so like that's it. And finally, there are like these people, like they helped me a lot throughout my PhD. So my professor Biswas, he helped me guiding technically as well as personally, like throughout. I have one mentor, Parthapatim Chakraborty from IIT Kharagpur, who guides me mostly on the time series prediction part, and he is a good reviewer as well. Then thanks to my PMRF internal reviewer as well as external reviewers for kind of critically evaluating my work, and which helped me improve my results and also thanks to my intern collaborator to who helped me gain some industrial perspective of my work, and thanks to all the co-authors, interns, MTech students that I guided, and my like all the IIT lab members. Special mentions to my mom, dad, my friends here at ISC, and PMRF and dark funding agencies. So thank you everyone. This was